Right now, a huge part of your computer is sitting on something that has no moving parts, no spinning disk, and no visible sign of how it remembers anything at all. Your files, your games, your operating system, your browser history, your photos, your downloads, all of it can live inside a thin slab of silicon that looks far too simple for the job it is doing. And that is the first mistake people make. They look at an SSD and think it is just a faster hard drive. It is not. It is a completely different kind of storage, built on a much stranger idea. A hard drive stores data with spinning platters and a moving read head. An SSD does not need any of that. It stores information in memory cells that trap electrical charge, and those tiny charges represent data. That sounds almost too simple until you realize what it means. The drive is not remembering your files by keeping them physically written somewhere on a spinning surface. It is remembering them by holding charge in microscopic cells that can be read later, even after the power is off. That is the trick. The file is not sitting there like a little object. It is encoded in the electrical state of the storage itself. And this is where the first layer of hidden engineering appears. The data inside an SSD is not just dumped into one giant open space. It is arranged into cells, pages, and blocks, and the controller inside the drive is constantly managing where everything goes. You save a file, and the SSD doesn't just drop it in. It decides where that data should live, how it should be distributed, and how to keep the drive functioning efficiently over time. That controller is doing a lot more work than most people ever realize. It's like a librarian, a traffic controller, and a repair crew, all rolled into one tiny chip. If you enjoy these kinds of hidden system breakdowns, that's exactly what this channel is built around. The parts people use every day usually have the weirdest stories underneath them, and SSDs are a perfect example of that. What makes SSDs feel so fast is not just that they are electronic, it's that they don't have to wait for anything mechanical to move into place. No spinning, no seeking, no arms swinging across a disk to find the right spot. Traditional hard drives lose time because they physically have to move. SSDs skip that entire problem. They can access data far more quickly because the information is stored electronically, not mechanically. That's why your computer boots faster, opens programs faster, and feels more responsive when it uses solid-state storage. But speed is only part of the story. The more interesting part is that SSDs are not immortal. In fact, they wear out in a way that feels almost unfair. Every time data is written, cells experience a tiny amount of stress. Over time, that stress builds up. The drive can keep working for a long time, but it's not endlessly fresh. It's constantly balancing performance against wear. That means SSDs are fast, silent, and efficient, but they are also finite. The same design that makes them quick is also the reason they eventually age.
And that leads to something most people never think about. When you delete a file from an SSD, the drive does not always immediately erase it in the way people imagine. Instead, the storage system has to decide what data is still useful, what can be cleared, and when it is safe to reorganize the memory. That process is handled by the controller, along with background tasks like garbage collection and wear leveling. Wear leveling is especially important because it spreads write activity around the drive so one area does not get damaged much faster than the others. The SSD is constantly trying to keep itself healthy while also making room for new data. It is not just storing files, it is managing its own survival. And that is where the real picture starts to sharpen. The SSD is not a passive box where files sit and wait. It is an active system that rearranges, balances, and protects data continuously behind the scenes. It has to because the storage medium itself changes over time every time it is written to. So while the user sees a simple folder, the drive sees a living workload that needs to be organized with precision. The other thing that makes SSDs so important is how they work with RAM and the CPU. When a computer feels fast, it's not because one part is doing all the work alone. The CPU needs data quickly. RAM holds active data in temporary memory. The SSD stores everything long-term. So the SSD becomes the place where files survive when the power is off, while RAM acts like the short-term workspace, and the CPU keeps everything moving. Once you understand that relationship, the whole machine starts to make sense. Each part has a different job, and SSDs are the part that makes permanence possible without the old mechanical delay. That is why SSDs changed everything. They didn't just make storage faster, they changed how the computer feels from the moment it turns on. They removed the loud mechanical delay that made old drives feel heavy and slow. They made loading screens shorter. They saving and opening feel more immediate. They turned storage from a waiting game into something close to instant access. And the deeper you go, the more impressive it gets. A device that looks like a simple rectangle of silicon is actually doing constant charge management, data allocation, wear balancing, and recovery work so your files stay available when you need them. That's not just storage, that's controlled memory at scale. So the next time you save a file and move on without thinking, remember what really happened. The computer just asked a silent little slab of silicon to remember something after the power went away, and somehow it did. If you're following this PC series, the next hidden piece gets even more interesting, because once storage and memory start making sense, the motherboard enters the story, and suddenly the whole machine has to stop behaving like separate parts and start acting like one system.